Hello everyone. So welcome back to our latest lecture session. So let's review what we have been up to in the last session. I believe we have started discussed in greater detail anyway the reduction potential, and then applied it to a few different kinds of examples, right? And I guess the basic case is PE is equal to PE naught, right, minus 1 by n log q dash, right? And obviously this would be applicable for which kind of reaction now? Most obviously, but we looked at different cases. One would be oxidized form accepting electrons and being reduced to its reduced form, right. So for this particular case, or for any generic case too, we can apply this reaction of P equal to P naught minus 1 by n log q dash, right. And then we try to visualize the system in terms of concentration on the y axis and P on the x axis, right. For that, obviously the reference was your P naught, right, and that's similar to your pH and pKa graph that we looked at. So let's just summarize that again. So what we looked at? Concentration here and PE here, right. So obviously if I try to represent this, and what is Q dash here? So I am going to write this as PE naught minus 1 by n log activity of the reduced form by activity of the oxidized form, right. So that is what we have here. So how do I write this? We know that the reduced form is going to be something like this, A reduced, and the oxidized form is going to have this behavior, A oxidized, right. And when would both these particular what do we say, concentrations or activities be the same? When PE is equal to PE naught, right. So and then we looked at those particular cases when we also had H plus, right, and also when we had the other elements present and so on. But the take home message was when the PE is low, right, and especially with reference to your PE naught, what does it mean? It would mean that reduced conditions would prevail relative to equilibrium, and that is in this particular region obviously when PE is less than PE naught, right. And also we looked at the other case when PE is high or PE is greater than let us say PE naught, right. So PE minus PE naught is high. So what did we look at in that particular context? We know that the activity of the electrons is going to be lower. That means obviously the oxidizing conditions would prevail, meaning you would have the oxidized species predominating, and that is what you see in this particular region. Yes, again this scale is obviously not to graph. So now let us move on. So we can understand let us say looking at the PE or P naught W values and so on, what it is we understand about the system at equilibrium, right. So now we are going to look at, let us say, understanding the system feasibility. So I am going to look at the PE of two half reactions, right, and then I will need to be able to figure out, let us say, which reaction will stay as the reduction half reaction and which one will stay have to be transformed as the oxidizing reaction. As in what am I talking about here? So let us consider two particular half reactions, stoichiometric of A plus A, right, plus let us say N1 electrons goes to, let us say, its what do we say, reduced form B, right, and let us say this has PE 1 naught, okay, and K1, and let us say the relevant other half reaction is C times C plus and 2 electrons goes to VD D. Anyway, stoichiometric coefficient of A, stoichiometric coefficient of B, stoichiometric coefficient of C and stoichiometric coefficient of D, and the relevant reduction potentials, standard reduction potentials, and K2 equilibrium coefficient values, right. So here we have two half reactions, right, but we know that let us say for a particular redox reaction to go through, you need to have not just the reduction reactions, which both of these are reduction reactions, as in they are accepting the electrons and the reduced forms are being formed here, right. It is acceptance of electrons, so that is more or less nothing but reduction. But as you know, you can never have both just two reductions, right. You will need to have both a reduction and an oxidation taking place simultaneously, right. You need to have a transfer of electrons. So now let us say I need to be able to figure out, looking at my particular values of PE and 1 and PE 2, right, and having the values of PE 1 naught and PE 2 naught, let us say, or K1 and K2, how can I, let us say, understand which particular half reaction will stay as written, as in which half reaction will go as reduction and which one needs to be reversed and be written as or considered as oxidation, right. So, one of these half reactions needs to be swapped, right, because that means it needs to be written as oxidation. So, for now for my particular case or for our particular example, right, let us consider that the reaction 1 is going to stay at as it is, as in reduction is going to go through, and let us consider the case when the second reaction is written as oxidation, right. So, in that case let us say what will my overall what do we say reaction be, and again now because I have different electrons I mean numbers of electrons involved here, right, as in N1 in one case and N2 in the other case, I need to multiply the second reaction by minus N2 and the first reaction by N1, right. So, again let us try to do that and have the overall half reaction, right, and what is that going to be equal to? I need to multiply the first one by N1 and the second one by minus, or the first one by N2 and the second one by minus N1, and why is that? Obviously, I need to be able to cancel out the relevant electrons, right, or the electron transfer needs to be the number of electrons being transferred needs to be the same. So, let me write that out here. So, it is going to be into N2 stoichiometric coefficient of A into A, right. We will go to N2 stoichiometric coefficient of B times B, not into, pardon me, right, times B, and here I am going to have plus stoichiometric coefficient N1 times stoichiometric coefficient of D, right, and here I am going to have again N1 times stoichiometric coefficient of C, right. So, this is my overall what do we say reaction now, right, and I need to be able to understand this particular system, right. So, let me also write down P1 and P2 values here. So, P1 is going to be equal to what now for the non-modified or unmodified half reactions, I guess P1 naught minus what is this please, minus 1 by N1 log, right, and activity of B raised to its stoichiometric coefficient by activity of A raised to its stoichiometric coefficient. This is for just this particular half reaction, right, and same case for this, what is the P value? Let me write that down. So, P2 is equal to P naught of the second half reaction by 1 by N2, because N2 electrons are being transferred, minus log, right, and what do I have here? Activity of D raised to its stoichiometric coefficient, right, by activity of C raised to its stoichiometric coefficient. So, these are obviously your P1 and P2 values, and considering the case when let us say this particular reaction 1 goes as reduction and 2 goes as oxidation, I came up with this particular what do we say overall half reaction, right. So, what does that mean now? Let us say to be able to calculate the PE of this overall reaction, it is going to be equal to PE1, right, minus PE2, right, but I am also going to have to consider the case when what is this now? I multiply this by N2 and this by N1, right. So, let us look at that and take that through, I guess, right. So, the PE of that particular overall reaction is going to be equal to PE1 naught minus PE2 naught of these modified or these reactions. We are not going to expand upon that now because it is going to be erroneous. So, let us just understand that it is the difference in the standard reduction potentials, right, and what do we have here? So, P1 is equal to minus. So, now let us say if it is multiplied by N2, right, the electron transfer would be 1 by N1 N2, right, minus 1 by N1 N2 log, right, and obviously again if this particular half reaction is multiplied by N2, it is going to be the case when what would that be now? This particular case would have to be times N2 here, right, or to the power of N2, right, log stoichiometric activity of B by activity of A stoichiometric coefficient of B times N2, right, stoichiometric coefficient of A times N2, right, plus 1 by N1 N2, this is from the second or from PE2, right, log stoichiometric coefficient of D raised to its stoichiometric coefficient of D multiplied by N1, right, by C raised to its stoichiometric coefficient multiplied by N1, right. So, now let us say I want to look at it or simplify it further. So, here again we are requested or we request you not to just transform this because it is going to be erroneous. Let us just try to understand this particular set as the what is it now, the difference in the standard reduction potentials of these half reactions, right. So, if I say it is minus here 1 by N1 N2, right, will be and log, so it is still going to be activity of B activity of A, right, and here it is going to be equal to activity of C by activity of D raised to the relevant stoichiometric coefficient times N1, right. So, now let us again have a look at our overall half reaction, not half reaction, pardon me, overall reaction, and let me write that down here so that it makes better sense. N2 times mu A, right, plus N1 stoichiometric coefficient D will go to N2 stoichiometric coefficient of B plus N1 stoichiometric coefficient of C, right. So, if we look at this particular reaction, right, and look at this set of variable here or variables here, what is that equal to now? You see that is nothing but equal to Q, right, Q for this particular overall reaction, yes. So, again what is Q here? Q is nothing but activity of B raised to its stoichiometric coefficient, which in this case is N2 times mu B, and activity of C raised to its stoichiometric coefficient, right, which in this case is N1 mu C, by activity of A raised to its stoichiometric quotient, which is N2 mu A, right, times D raised to its stoichiometric quotient, which is N1 times mu D, right. Again, as we see, this is nothing but equal to this particular variable, right. So, now I can write PE of the overall reaction as the difference in the standard reduction potentials, right, minus 1 by N1 N2, right, log Q, right. N1 N2 is obviously the number of electrons being transferred, right, that is what we saw earlier when we tried to modify the two half reactions. So, N1 N2, Q is the relevant ion activity product of the overall half reaction, right. So, here we did say that this is just the difference in the two standard reduction potentials. There is a particular reason why you can't just expand upon it as 1 by N1 N2 log K and get that done. You should try that out, you will see that it is going to be erroneous. Let us see how we can get that, I guess. How can I get the overall K value? So, I am going to look at log K. So, for the particular first half reaction, I know it the equilibrium quotient was 1, let us say, for 2 it was K2, right. And how did I get for the overall half reaction? To do that, I had to multiply K1 by N2 and K2 by minus N1, right. So, obviously, we know from what we did a couple of sessions ago that it is going to be nothing but equal to what now? N2 times log K1, right, minus N1 log K2, right, and this is something that is logical too and something which we looked at a couple of sessions ago, right. So, from here though, again I know that PE1 naught is equal to what now? 1 by N1 log K1, right, and I know that PE2 naught is equal to 1 by N2 log K2, right. This is something that I know, and obviously what does that mean? That means log K1 is equal to N1 times PE1 naught and log K2 is equal to N2 times PE2 naught, right. So, what does this transform into, right? This particular equation, how would that transform into? Log K of the overall reaction, K of the overall reaction is nothing but N2 times N1 P naught, N2 times N1 P naught, right, P1 naught minus N1 times N2 P2 naught, right. So, that is equal to N1 N2 times P1 naught minus P2 naught, right. So, substituting this particular expression that we have in our earlier equation, where we had let us say log q here and p here, right. I am going to substitute this particular variable here, and let us see how it is going to transform into now, right. So, we end up with P e is equal to 1 by N1 N2 log k minus 1 by N1 N2 log q, right, and now it is taking a familiar shape. So, P is equal to 1 by N1 N2 log k by q, right. So, I guess I should not have written it as P e, I should have written it as P1 minus P2, right. So, let me continue writing that. That is a better way of expressing it, right, or the correct way, let us say P1 minus P2 equal to 1 by N1 N2 log k by q. So, now I guess we are at a stage where we can try to understand the system. Anyway, I guess we looked at the relevant basic derivation, but you do not obviously need to mug that up, but you need to understand how to be able to understand the basics here, right. So, obviously, what were the assumptions we looked at? We looked at the case when the half reaction 1 is written as reduction, right, and reaction 2 we considered that to be the oxidation, right. That is why we multiplied that by minus N1, right. So, again in that case what is it that you see here? When will P1 or when P1 is greater than P2, right, what do you observe here? You observe that K is greater than Q, right. So, P1 greater than P2 means this is positive, and would that be the case when K greater than Q or Q is less than K, right. Again, what does this mean now? When Q is less than K, you know that the forward reaction will be favorable, right. Forward reaction is favorable. And how did we write the forward reaction, or how did we get this particular forward reaction? You remember that we consider reduction to be the half reaction 1, but we swapped the second half reaction as oxidation, right. So, again this case obviously works out as you see, right. When will P1 or when will this particular reaction be feasible? When Q less than K, right. When Q less than K or when K is greater than Q. Obviously, when K is greater than Q, what does that mean again? You know, inversely here it or conversely it means that P1 is greater than P2, and obviously where did that come from again? From considering that reduction is half reaction 1 and oxidation is half reaction 2, and only in that context will we have the forward reaction as feasible. So, again let us try to understand what we have here. So, what it means is that when you have two half reactions and one of the half reaction is greater than the other, let us say in this case we are talking about P1 greater than P2, right. So, we had two half reactions, right, and one case P1 and the other case P2, right. And when did we see that the reaction would be feasible? So, let us say if P1 is greater than P2, right, what would be the scenario when this particular reaction or redox reaction would be feasible? It would be the case when 1 stays as reduction, right, but 2 is considered as oxidation, right. So, obviously, what does this mean now? When P1 is greater than P2, we will consider 1 as reduction itself, right, or as the half reaction stays as it is, but the second case or the second or the lower P2 value, or because of the lower value we will have to see to it that it is considered as oxidation, right. So, again that is the particular case. Obviously, if P1 less than P2, when will the redox reaction be feasible? When 1 is written as oxidation or considered as oxidation and 2 is considered as reduction, which is the way we write it anyway, right. So, we need to now compare two P1 and P2 values, let us say, or the P values, the two P values, and then we can identify, let us say, which reaction is going to go forth as reduction and which reaction is going to go forth as oxidation, right. So, in this context also let us try to look at one particular graph here that I have, right. So, here let us say let us try to understand the system here, let us say. So, similar to the example that we had here, we have let us say two redox couples, one A reduced and A oxidized, right, A reduced and A oxidized, right, and also B reduced and B oxidized, right. So, let us just write that down here. So, A oxidized plus N1 electrons goes to A reduced, right, similar to let us say reaction 1 that we looked at, and not A, pardon me, B oxidized plus N2 electrons goes to B reduced, right. And here I have this concentration versus PE graph, and we have both the relevant pieces of information here though, right. And here let us try to understand a particular scenario, let us say, right. Let us try to consider the case when let us say the second reaction is goes as oxidation, okay. So, what am I considering here? I am considering that here one will proceed as reduction, right, and 2 will go forth as oxidation, as in this has to be the inverse of this particular half reaction. So, let us try to consider that case, I guess, right. And then let us consider the two cases when let us say I have PE1 let us say to be somewhere here, let us say PE of A, right, this is the case, and PEB is let us say somewhere here, yes. So, let us say this is my case here, right. And now let us say I am going to consider that it goes through as oxidation here, right. So, let us see if that is feasible or not feasible or so on now let us say, or let us say let us look at one particular case here. So, let us say now I say that when PE1 is less than PE2, right, that is what you see here. In this case PE1 is less than PE2, right, but I am saying that PE2 is going to go through as what is this now, oxidation now, right, or the reverse reaction for this particular half reaction is going to go through. So, what does that mean? That means obviously your concentration of your oxidized form of B is going to increase, right. So, as the reaction goes through, initial concentration of B oxidation B in its oxidized form is here, and let us say because it is oxidation reaction or the inverse of this, not inverse, I guess the backward half reaction here, right. So, then obviously as you see the B oxidized form is going to increase, right, and obviously you would see that the B reduced form is going to decrease, right, that is what you see. And obviously then where will the PEB shift? It is going to keep shifting to the right, the PEB value is going to shift to the right. So, obviously now let us understand what is going to happen with this particular PE1 case, I guess. So, here if we consider that one stays as reduction, right. So, if it stays as reduction as in this forward reaction is feasible, what does it mean? As it goes through or goes forward, A reduction increases and A oxidation decreases. Let us try to plot that here. So, A reduction increases in this direction, right, and A oxidation decreases in this direction, as in PE of A is moving in this direction, right. So, what do you see here? PEB is moving out here and PEA is moving out here. So, they are never approaching each other, right. So, which is not going to be the case, right. Your particular system would try to approach or as in come to a particular equilibrium, let us say, but when do you know that equilibrium will exist? That will be the case when PE of A is going to be equal to PE of B, right. So, for that to be the case, in which direction should these particular values of PEA and PEB travel? They need to travel towards obviously each other, right. So, obviously what does that mean? Our assumption, initial assumption of 1 going as reduction and 2 going as oxidation will take the system away from equilibrium, right. So, that is not how it is going to go through in nature. So, it wants to what we say reach equilibrium, right, or PEA needs to be equal to PEB, right. So, in that case what is it that we need to observe? We need to consider that 1 would go as oxidation, right, and 2 would go as reduction, right, in this particular case. And why is that? That is because PE of B was greater than PE of A, right, and that is similar to what we discussed earlier too, right, as in PE1 minus PE2 is equal to 1 by N1 N2 log of K by Q, right. This is what we discussed earlier. So, if I write this as PE of A minus let us say PE of B equal to 1 by N1 N2 log K by Q, right. but we know that P of B is greater than P of A, P of B is greater than P of A. So, that means this is a negative value, that means what now? Q is greater than K, right. That means reaction is infeasible, right. So, obviously, when is the reaction feasible? Let us see that when 1 which is A oxidized plus N1 electrons goes to A reduction is inverse and written as or considered as oxidation, right, and 2 which is A not A pardon me B oxidized plus N2 electrons goes as goes to B reduction and it is written as or considered as reduction, right. And why is that again? Because the P of B is greater than P of A, and that is what you see from our particular starting case here, right. And now let us consider this particular case. Obviously, when P of B is considered as reduction itself, the case with respect to B, and the case with respect to A is considered as oxidation. So, let us say for B, let us work it out. If it goes as reduction, right, what is going to happen now? The B reduced form is going to increase as in this, it is going to go in this direction, and B oxidized form is going to decrease. So, it has to go in this direction, right. So, that means this particular PEB is going to shift in this particular case, and same case for A. Let us say what needs to happen, A oxidized form needs to increase because it is written as oxidation. So, in which context or in which particular scenario will that increase? As you see, it is in here. So, it needs to travel in this particular direction, and obviously the reduced form is going to decrease when oxidation occurs. So, it is in this direction, right. So, here, and so when PE and PE A and PEB meet, let us say at one particular scenario, when PEA is equal to PEB, obviously that is when you will have equilibrium, right. And I guess what was the starting point of this particular scenario, that PE of B was greater than PE of A. That is why we had to write for B case it would be or stay as reduction, and for A case it would stay it would have to be written as or considered as oxidation, right. So, that is something that we have to understand. So, we are looking at two particular cases here, right, or two sets of half reactions. So, how do you determine the reaction feasibility for the overall reaction? So, the overall reaction would be feasible when that half reaction whose reduction potential is higher is written as reduction, or in this case PEB, because it is higher than PEA, it is going to be considered as reduction, right, and that half reaction whose reduction potential is lower, or in this case PEA, right, that is from my starting points here, right, is lower, will be considered as oxidation, and only then will your overall reaction be feasible, right. So, I guess that is our particular what do we say session for today, and I guess I am going to look at the relevant applications from the next class or next session, pardon me, right. So, we are going to try to bring everything together in the next session, as in if you remember, I guess we considered initially only what do we say now, acids and bases, and then looked at complexes, precipitation, and then reduction potential. So, the next couple of sessions anyway should be able to bring everything together in a pretty what do we say good manner, let us say, if I can, that how is it all these 3 or 4 environmental processes relate to each other, right. So, let us take that through in the next couple of sessions, I guess, and I guess, but for today I am done, and thank you.